Hello everyone, welcome to OdinSchool. Today we are going to learn about few of the very important concept and a distribution in statistics. In the advanced statistics course, chi-square test and distribution plays a very vital role. We will understand why and how. Before that, let's first understand the primary question. Why should someone learn statistics? Statistics is one of the most widely used subject in both professional as well as personal life. Talking about decisions, any decision that we take in real time. Say for an example, I am looking for a job and then I've given a couple of interviews. I've cracked both of them and I have an offer in place. I have offers from both the companies. Now I have to decide which company I should choose, and how am I going to decide which company should I choose? Now I'll look out for the CTC. What is the company that has provided me the maximum number, and what are the benefits that I'll get if I choose a particular company? So I'm going to quantify my quantify the advantages of joining a particular company and try to decide on joining that particular organization. Statistics is everywhere in real life. For every single thing that we do, we take decisions. We take several decisions in a day. All these decisions are backed by statistics. So statistics helps in both professional as well as in personal life. In a business also, if I have to know whether there is a particular area of improvement in my business, or what is the area that I'm performing really well in my business, I cannot understand the business without performing statistical measures on the raw data. Raw data gets converted into useful information only by the application of statistical measures. So it is really vital to learn about several types of statistics that are present and correlate it with the business to try and help business. That is the idea. So hence learning statistics becomes vital. Let me quickly introduce about OdinSchool and as well as about me. OdinSchool is a technology upskilling platform. They help us continuously acquire new skills. Their motto is to stay skilled and stay ahead. Whereas about me, I'm Gautam Kumar Jayachandran. I have 6+ years of experience as a senior data scientist. I work with several technologies in my daily work. I work with Excel, SQL, Python, Tableau, Power BI, and Alteryx as well. I have worked with several domains as well in the past. Now currently I work in financial domain. With that said, let's understand the agenda for today. We are going to see only two topics, chi-square test and chi-square distribution, but we are going to see in depth of both these concepts so as to understand how easily we can derive the logic and how can we implement the logic into a business data set. We will create data set, we will apply one factor chi-square test, we will also perform two factor chi-square test. In chi-square test, there are a couple of methods apart from the one factor and the two factor that I said. There is a test of independence and there is a goodness of fit test. We are going to see both. First, let's understand the concept theoretically. Chi-square goodness of fit test evaluates if a sample data matches a population. It is as simple as that. Say for an example, I subsetted data from the population and I claim that the sampled or the subsetted data is of Poisson distribution. If I have to verify whether it is of Poisson distribution or not, I have to evaluate it with the population and understand how the expected and observed frequency differs. If it differs, then it means the distributions are not the same. If it is not differing, it means the distribution is same. I'll show them with an example, just a theoretical understanding here. So chi-square of independent of test compares two variables in a data in a table and see if they are related. So it tests to evaluate whether distributions of categorical variable differ from each other or not. Again, it tells us about the correlation between categorical variables. You must be very clear here. You cannot claim chi-square test to be a test for calculating the correlation between two numerical variables, because for numerical variables chi-square will not work. Only for categorical variables chi-square will work. A very small chi-square test statistic means that your observed data fits your expected data perfectly, which means there is a relationship. If the chi-square test statistic is very large, then it means that the data does not fit well very much within the relationship. Basically, it will not correlate well with the population. This is a theoretical understanding of it. We are going to see a lot of examples, but before that, let me tell you how to derive chi-square test and then I'll explain you, because in Excel it is going to be only one function. If I just ask the machine to give me a chi-square test function, the output will be generated. But we need to know how to generate this output with the help of certain concepts. Now first let's understand. Yeah, first let's understand what is, how can chi-square test be. Chi-square test. Now in chi-square test, in chi-square test, first few things we need to know. We might have data, which is basically population, and now you subset the data, which is basically the sample. Then what happens is, if I have to correlate or understand whether the distribution in my sample is belonging to my population or not, I have to perform a chi-square test to understand the same. Now in this case, what I'm going to do is, I'm going to explain you what are the data that we will have, what are the data points that we have, and what are the terminologies through which we can actually calculate the numbers. The first thing is calculating the sum of square differences. Basically, chi-square test is simply nothing but mathematically it is basically the difference of, sorry, this is a square difference, basically square difference of sum of squares. This is the mathematical understanding behind chi-square test. Let me show you that with syntaxes. Now we have data, which is the observed frequency or observed information. Okay, this is denoted by O. Then we are expecting this to be very much related to a particular value. This expected frequency or expected info is denoted by E. Now you might ask, how can I calculate expected information or frequency? I'll show you how to do calculate the expected frequency or not. Only if you have these two things, then the formula will be like observed frequency minus expected frequency the whole square, divided by expected frequency. So if I just put this in the middle, so this is exactly my formula for chi-square test. Now in this case, we must understand how to calculate the expected value. The expected value can be calculated very simply. It is basically nothing but the total of rows, I'll say T small r, basically total in the rows minus total in the column. This is my expected number. This has to be divided by, I'll just, yeah, this has to be divided by the total value, total observed value, which is TO. T small o. So basically expected value can be calculated by substituting the total in the rows minus total in the columns divided by total observations, total occurrences of the observations. Now it might be theoretically a little confusing, but it is very easy when we apply this in Excel or any other tool to generate an insight out of it. In order to do it, what I'll do is, I'll try. Maybe we can take an example, basic example first. Then we will see what is. First, let's see goodness of it. Then we will take test of independence. In test of independence, we will see one factor test of independence and two factor test of independence as well. Now, for basic understanding, now how do I calculate this expected frequency? Now, when it does not change the value, if say for an example, I'm rolling a dice. I'm rolling a dice. Now I am believing that, say for an example, I'm rolling the dice 120 times. There are 6 sides to a dice, right? So what happens is, the expected frequency would be, I would simply say expected frequency for the dice side 1. For the dice side, 1, 2, 3, 4, 5, and 6. The expected is when I'm rolling a dice 120 times, I expect it to have equal proportionality. So 120 divided by 6 sides will give me the expected value for each and every uh, dice side. You will have 20 percentage chances, not 20 percentage chances, 20 times occurrences of values in each and every instance. Every time I throw this dice out of 120 times, I expect the machine to give me 20 times for each side, but the observed value after the conducting the experiment might be little different. The observed value might be something else. It can be 20 for first instance, 25, 22, 15, 12, and the remaining whatever it is. So this becomes my observed. In this case, this is my population and this is my sample. Now I have to compare whether the observed data and the expected data are correlated to each other or not, whether all the dices are having equal chances or not. The question remains the same at the high level. We need to understand whether rolling the dice 120 times will return me equal chances for each and every side in my dice or not. Let's take this example. This is an example for the goodness of it. Let me show you with an example. Okay, first let's create a data set dice and then expected frequency. Then I'll take observed. Perfect. So let me simply format this. Okay. We have dice, we have expected frequency and observed frequency. Okay, perfect. 1, 2, 3, 4, 5, 6. Perfect. This is the sides of the dice. The expected frequency is what? Assume that I'm conducting the experiment 120 times. I'm just putting this line. Rolling the dice 120 times. Okay. Now the expected frequency is, how can we calculate this? This is simply nothing but 120 divided by 6. Total number of times is 6. 6 dices. So what I'll do is I'll keep 20 for each and every sides. In this case, this is only one factor, so we can directly calculate the expected frequency, total number of incidences by the unique number of experiments. So we have 20 times. We are expecting the dice to roll or present 20 times if I'm rolling the dice 120 times. Now let's see what will be the observed frequency. It should be anything between 20 to it can be anything between 0 to 120, but we want the overall sum to be not exceeding 120. That is something that we have to do. So I'm going to do some data manipulation here. Looks like we have huge number of values, but we should not have anything greater than 120 in this case. So what I'll do is I'll convert this 80 into 8, this also into 8. This would be in 10 times This again will be 8, again will be 8, this will be 20. Now we have 60 deficit. So what I'll do is I'll try to distribute the data. I'll keep 18, 18, 20, 18, 18 and 20 we still do not have, so I'm going to increase the bandwidth somewhere else as well. This will be 22 and this can be 23 and this can be 17. That way we will have observed frequency in total 120, summing up to 120 incidences. Now that we have this data randomly generated, we did not have any control over it. Let's define our hypothesis. Null hypothesis. Let me just format things. I'll just keep it in this format, which is denoted by H naught. What is going to be our statement? Our statement is going to be all the 6 sides will be equally distributed. Okay, or will, I would say, will be equal to the expected distribution. Perfect. So what happens here is I'm just trying to create a null hypothesis. The null hypothesis that I'm trying to define is all the 6 sides will be equal to the expected distribution. Whereas what is our alternate hypothesis? Our alternate hypothesis is going to be just the opposite of null hypothesis. It's going to say no, not all the dices, all the 6 sides of the distribution are equal to each other. We will say here, we will say expect observed frequency or distribution, I would say, that way it is easy to understand, will not be equal to expected distribution. Okay, this is denoted by h of 1 or h of a. I'm just keeping it h of a. Let me format this nice and clean. Perfect. So we have this information now. Now in this case, what we have to do is we'll have to either reject null hypothesis or accept alternate hypothesis. I mean, like, both are same only. If I reject null hypothesis, eventually we are going to accept alternate hypothesis. So let's see how this can be done. Now I have two sets of value. If I have to compare these two sets of value and see if they are fitting pretty much together, what I'll do is I'll write, I perform a goodness of fit. Chi-square test. Okay, in this case, what I'll do is I'll try to perform the chi-square test and generate a value. Remember, one thing that you need to know is chi-square test will always retrieve the p-value only. What is the p-value? The probability of rejecting null hypothesis when it is true. This is the idea of no, p-value. P-value simply says the probability, it is simply nothing but the probability of rejecting the null hypothesis when it is true. So basically what should we have? We should have very minimal p-value, which basically is if it is less than my alpha level. We spoke about alpha level and other things yesterday in yesterday's class. So in this class, I'm just not going to spend time in explaining the same thing, but the idea is the p-value has to be less than my confidence, so less than my level of significance. So level of significance, generally speaking, it will be, we consider it to be the ideal number to be 0.05, basically 5%. So I'm just going to keep 0.05. So what does it mean is, if the p-value is less than the um, what is this, alpha level, or basically level of significance, then we have very less evidence for the presence of null hypothesis. Okay, so this is the idea behind the p-value. I'm just going to keep it here. Perfect. Okay, we have this theory for p-value. Now let's calculate the p-value for this particular goodness of fit and try to generate an output out of it. What I'll do is I'll perform chi-square statistic. Perfect. So to calculate this, I'll use chi-test function. See here, chi-square test function is that there are multiple values are there. So in this case, we are going to see whether this is going to retrieve me uh, distribution between, not the distribution, basically the differences between these two groups. So in this case, this is my actual data is basically the observed range, and the expected range is this. Once we have this, we can simply close this and see what is the chi-square statistic value. This chi-square statistic value is basically the p-value. So I'll say p-value generated from the chi-test is, so here it says the generated p-value is 0.93. Let's round this. 0.93. In this case, what is the hypothesis? The hypothesis is all the six sides will be equal to the expected distribution. Now, how will I quantify this output? We already know this is the p-value. The p-value should be less than the level of significance, 0.05. So in this case, it is not less than 0.05. So what we will do is we see that p-value is lesser than the alpha level, hence we have strong evidence to the presence of null hypothesis. So we cannot reject null hypothesis because we have strong evidence towards null hypothesis. What is my null hypothesis? All the six sides will be equal to the expected distribution. Now, what does it say? It says the values are the expected values, as the observed values are very close to the expected values. Hence, there is no what I would say. Hence, there is no uh, there is actually good correlation. Basically, these two variables are very much correlated with each other. But the problem is not the problem, but the understanding is that they are not differing very much. If you see the values only, you can understand. For 20, you get 22. For 20, you get 17. The values are around 20 only. See what happens when I actually manipulate this data. I'll manipulate this data to very less values, 10, and then I'll change this into 9, 34. Mm, Instead of 23, I'll have 3, because randomly you will have the values, right? There will be majority in one side, there can be majority in another side. What's the frequency here? 121. So I'll just keep this into 19. Yeah, look at this. The p-value is now changed. Let's ask the machine to give me the 4 digits. 4 digits also is not giving us anything. Let's not round it then. So see here, 5.21 to the power of minus 13. It is very clearly 0.0005 point something, which means that the observed frequency is not close to the expected frequency. They are completely far away from each other. Hence, there is no relationship between them. This is actually test of independence. I'm sorry, I've written it as goodness of fit. This is basically test of independence. Yeah. Okay. So in this case, the expected observed frequency is independent of the expected frequency. However, we can go ahead and reject the null hypothesis, saying that observed frequency will not be equal to the expected frequency. This is one factor test of independence. There is one more way of one more way of performing to test of independence, which is basically you know two-factor test of independence. My chi-square test for a test of what is this goodness of fit also works exactly in the same way. It exactly does the same operation just like we did here. We will calculate the expected frequency, and then we will have our observed frequency. Then we'll calculate the p-value using chi-square test. Once you calculate the p-value using the chi-square test, we will compare the p-value with our alpha level. What is our alpha level? 0.05. In this case, it is less than 0.05. So we will say that reject null hypothesis. This is the idea behind the chi-square test of independence, one factor test of independence. Let's create a new sheet and create another example here. Let's create two-factor test of independence. Um, what example can I give? I'm just thinking about the example. For two-factor, I need data in both columns as well as in rows. So what we can pick? Okay, let me show you. Males, female, um, yeah, I'll say Pepsi, or maybe let's go with. I think going with politics doesn't help, so let's keep Pepsi, Coca-Cola, and Sprite, 7 Up. Now what I'll do is I'll create numbers. So between what I can say between 100 to 635, the mean should not be greater. The mean should be somewhere around 250. Standard deviation is 4 or 3. Let's keep it 3. Cumulative true. Okay, let's do it manually. I thought I'll do it with function. Random between two numbers. So I wanted it to be between 1 to 1000. Now assume the experiment have been conducted with 1000 people. People were asked how many of you like Pepsi, how many of you like Coca-Cola, how many of you like Sprite or 7-Up, and what is the total sum that we have. We will have the same thing here. But we have a huge volume, but we don't want this much of volume. Let's round it off to 1000. For 626, I'll keep 62, 65 something. Here it will be 95, 94, 75, 85, 77, 67, and 65. We have 623. We still have a good 77 places. So what I'll do is I'll change 65 to 350 divided by 8 should be somewhere around 4 times for me. I can add 40 in everything. So I'll just go 45, 135, 134, 115, 125, 117, 107, and we have 105. We have 943, another 57. 57 divided by 4, 8 should be 8. 8 of 64. Before that, we will have 58. So 7, I can add in everything. So I'll just add 112, 142, 141, 121, or 22 something. We can add it over there. Here I'll just add 132, 122, 102, 14. I can add 112. 996. I'll just keep 116. So 1000. Perfect. So we have created this data. I'm just trying to show two-factor test of independence so that we will be able to understand how things work. Something happened here. Let me close my Epic pen. Perfect. So let's highlight this. Okay, let me quickly copy this or save this file and try opening it. So I'll simply say Chisquare Test. Okay, perfect. So let's format this. Not working. Okay, let me close this and reopen it one more time. So in the meanwhile, I'll explain. So what I'm trying to do here is I'm trying to see whether the gender has any contribution or any relationship to the products that they consume. If yes, then we will have to think about selling different products for different gender. If no, then we'll have to try improving the product based on some other feedback. So that will be the idea behind performing this test. Now if you see here, we are basically having two different dimensions. One is a dimension of gender, another is a dimension of uh, products. So gender and the products. Perfect. I'll just keep it as it is. Now let me quantify this. I'll keep it in white and change the background to dark blue. Perfect. So we have gender and products. Let's define our in this case, let's not take the help of any functions. Let's derive it by ourselves. If we have to derive chi-square test of into independence for two factors, we need to know two things. First, we need to know what will be the expected value for both the genders. Then what else do we need to know is we need to calculate chi-square statistics. Finally, we need to know degree of freedom. So we know how to calculate expected values. We also know how to calculate chi-square statistics. Chi-square statistics is basically the expected value in both the sum of expected value in both the male and female. I'll explain you how to do it. The degree of freedom is simply defined as row minus 1 into column minus 1. Again, this is the topic that we have seen yesterday. So I'm just going to continue explaining the math rather than the steps. Chi-square statistics is basically the sum of, as I explained in the first place, squared values. Expected values, we know it is basically O minus E divided by E. That is the idea behind so we need to calculate all these three values first. For us to calculate all these three, first let's take one step at a time and do it. Once we have the final value, we will compare this with the chi-square table to achieve the p-value. Using p-value, we can reject or accept the hypothesis. Now let's calculate the hypothesis first, or define our hypothesis. Null hypothesis. What is the null hypothesis? H naught. Gender and products do not vary. Hmm. Basically, gender and the products do not vary. What I would say, gender and products do not vary. That should be the case. So basically, it means that both the genders are drinking the same type of drinks, but that's not the case in our example. Now let's calculate alternate hypothesis. Alternate hypothesis is exactly the opposite of same. It is denoted by H1 or HA. It says gender and product varies. So basically every gender has a different choice of drinking. That is what someone is saying, but the general belief is that both the genders drink the same type of drinks. Now we have conducted this survey and we have the population information for each and every gender. Now in this case, first let's calculate the expected value for male. So we have this observed value which is coming from the survey. Now we need to calculate the expected value for male. I have some gaps, so we are going to multiply things here. We are going to do several steps. Expected value for female. We are going to calculate it for female as well. Perfect. Now in the first case, how do we calculate expected values? O minus E divided by E. O minus E, when I say it, is basically the rows minus columns divided by the total value. Now in this case, was expected value for Pepsi. For Pepsi, this is my, sorry, for male, this is my row level information minus column level information divided by the total values that we have. This is for Pepsi. Then I have to do the same thing for Coca-Cola as well. What is the row total? This is my row total divided by, sorry, row total minus, row total minus the column total divided by the overall value. Let's do the same thing here. We need to take for Sprite row total minus column total divided by this, and then we have row total minus column total divided by the overall population. We have the expected value for each and every product for male. That's it. Yes, perfect. Let's do the same thing for female as well. I'll just copy this and delete the values. For female, let's calculate this. The total for female is this minus this. So, okay, sorry, I did not divide it by 1000, which is basically our total values. Then let's do the same thing here also. Here it will be total of row total minus column total divided by the tables total. Same thing for sprite as well, divided by, sorry, minus this. Then let's calculate row total minus column total divided by table total. Let me validate the numbers. 74 minus B4, 75. Okay, perfect. Looks good to me. Here, let's validate the numbers. Yes, looks good to me. Looks good to me. Perfect. Now, I'm just trying to keep it in a very safe way by first substituting the columns and rows, then finally dividing it. Other which ways it will give us values that are random in nature. Yeah, perfect. We have the expected value for male. Let's calculate the expected value for female. Then let me do this fastly. Perfect. So we have the expected values and we also have the observed values. Once we have this, we will not be directly taking this. We will perform squared values for each and every expected numbers. In that case, what I'm going to do is I'm going to say O minus. So what we have done is first we'll have to do expected minus observed values minus expected value, I think, which is what we have calculated there. Then if I have to do it, I have to just square the values first. In order to do it, I'll simply say O minus E. Just keeping the format clean, that way we don't have to worry too much. Yeah, perfect. Perfect. Let's calculate the values for O minus E. Then we will calculate O minus E the whole square, then the substitute of it. Here it should be the whole square, sorry, divided by expected value. Then we will calculate the square of it. We'll simply square the values. Yep. Cool. Now let's have the calculation, the observed value minus this. We were able to calculate the expected values by substituting row minus column divided by the overall value, which is right. Which should be perfect. So if I'm validating, perfect. Now let's validate the numbers for male. Pepsi observed value minus expected value. This is simply observed minus expected. I can just simply pass this. So automatically the data dynamically gets picked up. Then what we need to do is we need to substitute this value with the expected value. This is our expected value. Once we have the observed value for expected value, what we need to do is we need to square this. to the power of 2. Okay, then what we have is we need to see what will be the values for here in female. It is 132 minus observed frequency, which is this. Then what we will do is we will substitute this with observed frequency, which gives us some information. Then square the values. So sum of squared values is my is the total understanding here. So if I have this here, you will have to okay, my bad, I did not square the upper portion, sorry. So here what should I have done is beaten to the whole square divided by this. I think this is wrong. Okay, perfect. Then let's validate the number with the formula one more time. The formula is O minus I observed minus expected to the whole square divided by E. Okay. Here what should I do is observed minus I should have calculated observed minus expected the whole square in this place. Just a second. Yes. The whole square. Then finally we will divide it by E, the whole square divided by E. Perfect. Yes, exactly. This is what we need to do. I'm just interchanging the logics here. Perfect. So I'll just simply square the difference that we calculated. Then what we need to do here is we need to calculate this value should be divided by the expected value here. We have a value altogether. So the observed value was 112, the expected value was 0.21272, and then it gets substituted here. Let's see what happens in this case. Yeah, I think no issues. I think this is correct only. Nothing. I don't want to confuse anything. I think apart from this, I need to just change the logic here. I have calculated female minus this. Okay, perfect. So what I'll do here is I'll simply take the value which is generated out of the calculation and square it. Here what I'll simply do is I'll take this and divide it by the expected value. We have this value, and then finally we will sum this. We will do the same summing operation here. This is the value, chi-square value, which is calculated by adding the chi-square statistics for both the samples, both male and the female. In this case, what happens is we know the chi-square statistics. We will not know whether this 5 lakh 4,268 is actually differing from each other, or from are less from each other. In that case, first we need to know the degree of freedom to see the value in the chart. So the degree of freedom is calculated by number of rows minus 1. 2 rows are there, so minus 1 into number of columns minus 1. So there are 4 columns, so 4 minus 1. So in this case, my degree of freedom is 3. So what we need to do is we have to go to the internet and figure out the p-value for this table from the chi-square table. From the chi-square table, since you know the degree of freedom, you just need to see what's the value that happens for that alpha level. So degree of freedom is in our case it is 3. So the degree of freedom is 3. What is our alpha level? Alpha level is confidence interval is 0.5, which basically gives us 7.81. So our p-value was 7.81 in the chi-square distribution table. With this value, what we can conclude is, or what we can understand is, Exiting the critical value. Yeah, okay, looks like it is all high. Okay, this is our critical value, and this is our p-value that we generated out of the machine. Then what we can do is we can also evaluate the chi-square test using I think we have done this manually, so we don't have to write it using calculations. So in this case, the p-value is greater than the alpha level 0.05, which is actually greater than the alpha level. Hence, what we will do is we will support null hypothesis. What is null hypothesis? Let's go there. Gender and products do not vary. So by calculating the expected value for mean and then calculating the for male and female separately and then squaring it and then dividing it finally gives you a result. That result can be used to correlate with the output that we generate out of null of chi-statistics. This chi-statistics can be then referred to the p-value that we generate from the chi-square table. If the p-value is greater than the alpha level, which is 0.05, then it means that you have to reject the null hypothesis, saying that no, genders and products do not vary with each other, they are all the same. Both the consumers consume equal there is no consumption difference in terms of gender. We can understand this by seeing the data itself. See here, out of 1,000 people, 500 male are drinking same products, whereas 484 males are drinking the same products. If you see that by product also, for Pepsi users in male is little high, which is like just 20 numbers, whereas in Coca-Cola also the 20 differences exist. Whereas in Sprite we have 37 as 27 as difference. In 7-Up it is just 5. So basically the difference is not very significant, and hence we cannot conclude that gender and by gender they do not choose product. Generally both the genders like to drink the same type of products. This is something that we can achieve with the help of chi-square. They are not independent of each other, they are actually dependent, not independent or dependent. Here the idea is to explain how good are they fitting into the population. Looks like they have really good correlation between them, hence there is no much difference between each other. This is the idea behind chi-square statistic. Let's see what is the other thing that is pending. Chi-square distribution. So the distribution also says the same thing, just using the same chi-square test function that we used in the one factor analysis. What we can do is we can take that analysis as an output and calculate the p-value. Once we have the p-value, then we can go ahead and accept or reject the null hypothesis. It is all about accepting or rejecting the null hypothesis, because generally a null hypothesis is a belief that the existing truth, the existing understanding of the data is true. But however, we wanted to evaluate it and validate it, saying that either it is true or either it is false. In order to do it, if it is categorical variable and if I have to do it with the help of an hypothesis, I can do it with the help of this one. I can do it with the help of chi-square test. Chi-square test is one portion or one process in hypothesis testing. We will be seeing other hypothesis testing as well in the advanced analytics portion. I think with that we come to the end of this class. Let me quickly recap what we have learned. Basically in this class we have learned very few things, which is basically chi-square test, and there are two types of test. One is one factor test of independence, another is goodness of fit. Goodness of fit and one factor test of independence works exactly in the same way. Talking about goodness of fit, test of independence for two factors, we will be trying to compare data that is coming in two dimensions. It should be present in both rows and columns, and we will try to evaluate whether both these dimensions are correlated with each other or not. If they are correlated with each other, we will accept the null hypothesis because that is the existing belief. But the alternate hypothesis might be, it might state that the relationship between these two categorical variables does not exist. So we'll have to try to evaluate this by with the help of chi-square statistic. We can take the same function chi-square and then calculate it using Excel, or we can use any other technology, Python. I don't think if I can do it in SQL, but we can do it in Python and all the other things. So we can evaluate it, and if the p-value is greater than the alpha level, then we will go ahead and reject the null hypothesis and accept the alternate hypothesis. In this case, the in the examples that we calculated, the p-value was actually greater than the greater than the alpha level. So hence we will not reject null hypothesis, because p-value indicates the evidence. It basically supports the presence of evidence of null hypothesis being true in the population or in the sample that we generated out of it. So that is pretty much is what we have learned in this class. Yep, thank you so much for joining this class. Please don't forget to like, share and subscribe to this channel. We will regroup for another topic tomorrow. Thank you.